Okay, this is General Physics textbook problem, page 220, number 43. This is a conservation of momentum problem involving a brick sliding down an incline, colliding with another brick inelastically, completely inelastically, and then sliding to a stop. We need to actually consider this in three different stages. Let's get the easy stuff out of the way first. All right, they give us the weights of the two bricks, which is fine, but we're going to need to find the masses because we're going to have to do some Newton's second law. We're also going to have to do some conservation of momentum, so we're going to need these numbers. Okay, the first thing that's going to happen is this brick at the top of the incline, M1, is at rest, and it has its weight acting downward, and it has a parallel component of its weight that's going to accelerate it forward. There's no friction, so I don't have to worry about force normal or the perpendicular component of the weight or anything like that. This 24.5 sine 30 is going to be F net that's going to accelerate the brick. Now, from kinematics, we have a V initial equal to 0. We have an acceleration. And ultimately, we want to find the velocity when it gets to the bottom of the incline. That's this V final squared minus V initial squared over 2a. And the problem is we do not know acceleration. But what we're going to do is we're going to go to Newton's second law. And we have this parallel component of the weight that's going to accelerate this brick down the incline. So we can substitute in the acceleration that we computed from Newton's second law. We know that the distance of the incline is 1 meter, so we can solve for this V final. All right, this V final is going to be the speed, the velocity that the brick, the little brick, the first brick, is at when it reaches the bottom of the incline and impacts the larger brick that is stationary. So its V final actually becomes a V initial right before impact. And that's what we're going to go to the second part of this problem, is it's now a conservation of momentum problem. So we're going to have the two bricks, they're going to impact, stick together, and then move away. So we're going to use conservation of momentum, and we have it set up for a completely inelastic collision. So the small brick, that V there, is the velocity at the bottom of the incline that we just got through computing. The larger brick is stationary. The masses combine, and then they move off together at some V final after impact. So this is the guy that we're after in this conservation of momentum part. Now this V final after impact then is going to be our initial velocity, and then we're going to slide to a stop. All right, so let's look at this sliding to a stop part. One of the things we want to know is distance. So I can go back to this kinematics equation here to compute the distance. The V initial is the same as the V final immediately after impact. Again, we have the problem, what do we do for acceleration? Well, we go back to Newton's second law, F net equal ma. In this case, it's the force of friction on these two blocks that are going to slide it to a stop. All right, mu k is given in the problem, or actually, no, the force of friction is given in the problem. This F net is given in the problem as being 5 newtons. So we do know all of this stuff. That is just simply 5 newtons. Now this mass, that is the combined mass of both bricks. We can get the acceleration, plug it in, and then solve for this distance to slide to a stop. Now the last part is time. How long does it take? Well, you can pretty much pick any one of your magic 5 to figure this out. I think this one is probably going to be the easiest. They slide to a stop. V final is 0. V initial is this velocity of the two bricks immediately after impact. We've already computed the acceleration from Newton's second law, so you can just simply get time. That's probably the easiest setup for that. And a very multi-step sort of problem. We have Newton's second law, we have conservation of momentum in an inelastic, completely inelastic collision, and some kinematics. So a nice problem involving lots of different concepts that you've learned throughout this whole semester.